Okay, we're going to look at another optimization problem, and this one is an important contrast with the last one. So it's very similar to the last problem I did, but enough important differences that the way we work it out and the test we use at the end is going to be a little bit different here. Okay, so we have kind of the same scenario. A rancher who wishes to construct two adjacent rectangular corrals of the same dimensions. So I have the same figure we looked at in the last video. This time, though, the total enclosed space is to be 2,500 square feet. What dimension should be used to minimize the amount of fence used? So in the last problem, our objective function was to maximize area, and we had a constraint about the amount of fence. In this problem, our objective function is about to minimize the amount of fence that we're going to use, and our constraint is about area. All right, so read the problem, whatever it's asking you to maximize or minimize, that describes your objective function. So we want to minimize the amount of fence, right? The amount of fence used, I'm going to have 3 sides of length y and 4 sides of length x that I'm going to use. My constraint is that the area, the total area here, which would be x times y plus x times y, or 2xy, should be 2,500 square feet. 2xy. Okay, so our objective function and our constraint. Next step in all of these problems is to solve the constraint for one of the variables so that you can reduce the number of input variables in your objective function. So this time I'm going to solve for y. So I'm going to divide through by 2x. And if I reduce that, I get 1,250 over x equals y. And my goal here is to put that into my objective function so that I have only one input variable in my objective function. So going back here to my objective function, I'll have 3 times this expression plus 4x. And then if I simplify that, I'll get 3,750 over x plus 4x. All right, so for my objective function, this is what I'm going to use. F equals, and I can write it like this. But if I'm going to take a derivative, I may want to rewrite this first term as 3,750 times x to the negative 1. That makes it a little bit easier when I think about the derivatives here. Okay, so this is the function I'm going to be working with. Let's talk about the feasible domain, and then we'll go ahead and find the critical points. All right, so this time when we talk about the domain, we're going to be talking about x. My objective function here is in terms of x. So we're talking about the domain. We're going to be thinking about what x should be. So x certainly should be greater than 0. If x is 0, then I don't actually have any rectangles here. But for this one, if I think about my constraint, and I think about lower and lower and lower possible values for y, so I make y smaller and smaller and smaller, and think about a biggest possible value x could be, we end up actually that when y gets smaller and smaller and smaller, x just gets bigger and bigger and bigger without bound. So there's actually no maximum value x could be here. Practically speaking, there probably is, but for this one, we really just have x greater than 0. So if you think about as y approaches 0 here, the x values would just grow without bound. All right, so we're ready now to find critical points. So you should know by now how to do that. Critical points for any function, whether we're talking about a word problem or anything else, derivative 0 or does not exist. All right, so let's look at our derivative here. We'll have negative 3,750 x to the negative 2 plus 4. I'm going to go ahead and rewrite that negative exponent in terms of what it means. Okay, so in the last problem, we didn't have any places where the derivative did not exist, but we do here. The derivative does not exist when x equals 0. And if I were just looking at a function equation here, I might think about that. In this case, though, that's not really part of our domain, so that doesn't actually end up being a critical point for this problem, so I can throw that out. And then the other thing I would want to think about is when this derivative is 0. So I'm going to set this derivative equal to 0 and solve for x. Okay, so every one of these problems is a little bit different. You just have to use correct algebra to make sure that you isolate the x. I might think about adding this term, 3750 over x squared, to both sides, multiplying through maybe by x squared, dividing through perhaps by 4 then. I'm just going to write out some of those steps. 3750 over x squared equals 4. Multiply through by x squared, divide through by 4, square root both sides. You'll get x equals plus or minus the square root of 3750 over 4. All right, the negative doesn't make sense in the context of the problem here, so we'll get rid of that and just keep the plus here. So we really only have one critical point in our feasible domain. All right, the next thing that we want to do is make sure that we test so that we can determine whether this critical point gives us the location of a maximum, a minimum, or neither. All right, and we talked about 3 different methods for doing that. We can look for absolute extrema on a closed and bounded interval. I do not have a closed and bounded interval here for my domain, so that wouldn't be appropriate for this problem. First derivative test, where you look at the sign of the first derivative on either side of your critical point to determine where the function is increasing and decreasing, so whether you have a max or min or neither. Or second derivative test, where you look at the sign of the second derivative. I'm going to use second derivative test this time just to do something a little bit different. Okay, so let's go over here, and for the test, we're going to look at the second derivative. So here's my first derivative. I'm going to go ahead and use that to find my second derivative. So when I bring down that exponent, negative 3750 times negative 2 will be 7,500 x to the negative 3, and then the derivative of 4 will be 0. All right, so here's my second derivative. What I want to consider is whether that second derivative is positive or negative at my critical point. Okay, so I don't actually need to plug in numbers to determine this. I might notice that my critical point is a positive value. So whatever a decimal approximation or simplified radical I get when I look at this critical point, that's a positive value. And when I plug that into this second derivative, that's going to be a positive value. So my second derivative will be positive, greater than 0, at that critical point, which tells me that my function is concave up in that region. So my critical point is the location of a local minimum, which is what we were after. We were trying to minimize the amount of fence used, so we have a local minimum. All right, so this x value is our critical point, which gives us a local minimum, and that is one of the dimensions of the fence here. So I need to go back over here and answer the problem. All right, so my x dimension is this. I'll probably simplify that. Okay, square root of 4 is 2. Square root of 3750 is not a perfect square, but 25 squared times 6 is 3750. So you can simplify that to be 25 square root of 6. That's exact simplified form. Our units of distance here are in feet. That's an exact answer. If you want a decimal approximation, you plug that into your calculator and you get a decimal approximation. I think you should get about 30.6 feet for the x dimension. I also need to find the y dimension. Y is 1,250 over x. So I'm going to go ahead and plug that in. 1,250 over my x value here. I'm just going to leave it in that unsimplified form for right now. Over 2. If you want to simplify that, you might notice that you can multiply by the reciprocal of the denominator. You get some nice simplification with the radicals there. You should end up with 100 over square root of 6. Once you've simplified that, that's your y dimension, feet for the y dimension. And again, if you want a decimal approximation for that, you get out your calculator, you get your decimal approximation. That should be about 40.8 feet. Okay, so the big deal idea here is that we had a very similar problem to the last problem, but because we were asked to minimize something different, the structure in the middle, what our derivative looked like, what our test looked like was a lot different. So you want to start the same way, but the key part is that in the middle, whatever happens with the derivative is what happens, and you keep following that through. All right, we'll look at some more examples.